Alright, in this video we are going to look at 2024 AP Physics Mechanics free response question set 1. Let's go to the first question. Here's the first question. Block A and B of mass m and 3m respectively are arranged in a setup consisting of an ideal spring with spring constant K and a horizontal surface. Friction between the surface and the blocks is negligible except in a region of length d, where the coefficient is mu. Also from the figure we can see that region and the coefficient mu. Block B is attached to a spring of length L and a negligible mass, as shown in the figure. Block A is held against the spring, compressing the spring at distance xc. Here is the distance xc. Alright. At time t0, block A is located at position x0 and is released from rest, which means at the beginning we don't have any kinetic energy. After the block is released, the following occurs. At time t1, block A is at x1 after traveling a distance xc. Block A moves with the speed v and the spring is at its equilibrium position. That means when the block reaches x1, all stored potential energy by the spring was converted to the kinetic energy of the block. At time 2, the left side of block A is at x2 after passing through a distance d across the region with non-negligible friction. So at time 2, the block A completely passed through the friction region. At time t3, block A is at x3 and block A collides with and sticks to block B. The word sticks implies that it's going to be an inelastic collision. Also, let's put time frames on the figure. So at the beginning we have got time 0, time 1 when the block reaches x1, time 2 when block completely passed through the friction region, and time 3 when block A collides with block B. Good. Here is the first question. For parts A1 and 2, express your answer in terms of givens and physical constants as appropriate. Derive an expression for the speed v of block A at time t1. Again, let's look at the figure. At time t1, our block A is going to reach x1, but it doesn't enter the region with friction. It just reaches the region. It reaches the region. It touched the region, but didn't enter yet. At this point, we can see that the spring potential energy is converted to kinetic energy of the block. So we can use conservation of energy. Energy initial is equal to energy final. Initially, we have got spring potential energy, half kxc square. Kinetic energy of the block, half. Mass of block is m. Speed square. 1 over 2 cancels 1 over 2 from the other side. The speed is equal to kxc square, or we can express it as xc times square root of k over m. Next. Derive an expression for speed v, a, and b of the two-block system immediately after the collision at time 3. Collision problems, we have to use conservation of momentum. But before going there, we have to figure out something. We have to figure out the speed of block A just before the collision. In the previous question, here, we found the speed of the block before it entered the region with friction. And logically, the friction is going to reduce the speed of the block. So first, let's figure out the speed when the block A passes through the region with friction. To do that, we can approach again the energy principle. Energy initial is going to be equal to energy final plus work done by friction. So here energy initial is not equal to energy final because we have got region with friction which is going to do work. Initially we have got again spring potential energy, half k xc square is equal to energy final v. Let's say it is mva. Va, here I mean the speed of the block after it passed through the region with friction. Square. Now, the frictional force here is going to do work, which is going to be equal to friction force times D. And let's open the frictional force. It's going to be coefficient times normal force, which is mg times D. Now, if we solve this equation, we will get VA is equal to square root of K xc square divided by m minus 2 mu GD all in the square root. Now we can go to conservation of momentum. Momentum before the collision must be equal to momentum after the collision. Before the collision, we have only block A moving. So we say mass of block A times speed of A is equal to, after the collision, block stick, so we can add the masses, MA plus MB, times their common speed, which is VAB. Now, block A has got mass of M only, block B has got mass of 3M, so if you add them up, it's going to be 4M, VAB, mass cancel, so we can see that VAB is going to be 1 over 4 VA. We can now bring this to the equation. Okay, next question. On the following axis, sketch a graph of kinetic energy K of block A as a function of time from time 0 to time 3. So on the figure again, let's show the time frames. Here time 0, time 1, time 2, and time 3. Okay, if it was kinetic energy versus distance, it would be much easier. But here we have got kinetic energy versus time, so we have to be extra careful. So let's start with the first region from time equals 0 to T1. Now, let's remember kinetic energy is equal to half mv square. The block spring system is going to oscillate periodically, so the speed is going to be changing as a function of sine theta. So the speed is going to be, velocity is going to be proportional to the sine theta. As a result, we can say kinetic energy is going to be proportional to sine square theta. At the beginning, we have got zero kinetic energy. At T1, we have got certain kinetic energy. And in between, the graph is going to change as a function of sine square theta from minimum to maximum. And you can use a graphical calculator, or you can just use your memory, where you will find that the sine square theta graph looks like S shape. From T1 to T2, we have got from T1 to T2, so it was from T0 to T1, right? So from T1 to T2, we have got constant force. That means we have got constant acceleration. And this acceleration is negative because it's going to be the force is going to be in the opposite direction of the motion. So as a result, we are going to have, let's write the equation for speed. Speed is initial speed minus acceleration times t. So kinetic energy is going to be half m v0 minus at square. So it's quadratic equation, and the kinetic energy is going to get reduced. So at the beginning it was this point, then this point, and it's decreasing as a quadratic equation like this. Now, from time 2 to time 3. I believe this is the easiest. No force, no acceleration. So V is constant. It's going to be a straight line. All right, next. Use principles of work and energy to justify the graph drawn in part B1 for the time interval from time 0 to time 1. Explicitly reference features of the shape of the graph you drew in part B1. All right. Let's start with work energy to justify our answer. Work is expressed as integration of force times delta x, which is also equal to change in kinetic energy. Because we have initial kinetic energy 0, we can just write k. So let's open this equation. So it's integration of force is mass times delta v over delta t delta x. From here we can see delta t over delta x, which we know as the speed. So it's going to be m v delta v. So it's going to be from 0, let's say we are reaching speed of v. So it's going to be m v square over 2 from 0 to v. So it's going to be half m v square, which we know as the kinetic energy equation. I already did it somehow here. I will bring it down again. Because speed is proportional to sine theta, work, which is equal to kinetic energy, is proportional to sine square theta. As a result, we are having the shape of graph shown above. Next, after the collision, the two-block system instantaneously comes to rest at time t4, which occurs when the spring makes a small angle theta max with the vertical as shown in the figure. For times t, which is more than t4, the system oscillates with frequency fl. The support holding the string is raised, and the procedure is then repeated using a new string of length 2L. Indicate how the new frequency of oscillation F2L of the system on the new string of length 2L will compare to the frequency of oscillation FL from the original procedure. So basically, what is the change? The length of the string doubled. If at the beginning it was L, it's becoming 2L. We know that the period of such oscillation, it's kind of simple pendulum, is expressed as 2 pi in the square root L over G. So when the length is going to increase, the period is going to increase, and we know that the period is equal to 1 over frequency. So when the length increases, the frequency is going to, the period is going to increase, the frequency is going to be decreasing. So it's going to be, the frequency 2L is going to be less than frequency of L. Let's justify it. In this system, period is equal to 2 pi L over G. Since frequency is 1 over period, frequency is inversely proportional to square root of L. As a result, So we can say that when the length is increased, the frequency is going to be smaller. All right, this is the end of the first question.